Hello everyone, let us continue our discussion. We are in week 11 and this is our lecture 4. So this week we have learned Castigliano theorem and we have already solved some example. Let us continue with some more examples. So example 1 today is a beam with a point load. It's actually a frame. So we have a frame like this and we apply a point load at the free end. So let this be A, B and C. Now for this problem, the length of the beam BC is given. So this is say A, and length of the beam AB is equal to say L. Our task is to find the deflection in the vertical direction at the point C. So this entire frame we can split it into two parts, as you can see on your screen, and the total bending strain energy is the summation of the bending strain energy in the beam BC and the bending strain energy in the remaining part, that is AB. So let us consider the part BC, and for this part let us consider a section at a distance x. So the moment at this point is P times x, and this is a hogging moment, so we put a negative sign. Now we can find out the bending strain energy, which is integral over 0 to A mx square dx divided by twice EI. So we have 0 to A, in place of mx we can write minus px whole square dx divided by twice EI. So we have p square divided by twice EI integral 0 to A x square dx. So if you solve this example, you have p square A cube divided by 6 EI. So the bending strain energy for the first part we have evaluated. Now we have to repeat the same for the second part. And for that, let us consider AB. Now, for this part BC, if we draw the bending moment diagram, what we have? We have PA at this end, and this is negative, right? So this is P times A. And the same moment will act here, and for the entire length, it will be same, right? So this is also PA. Now for this part, if we consider a section at a distance say y from the point B, for that we can find out what is the moment. So my is equal to P times A, and obviously this is also hogging. Therefore, the bending strain energy in the component AB is 0 to L, that is the full length. So we have m square y dy divided by twice A. So effectively we have 0 to L PA whole square dy divided by twice EI. That means we have P square, A square, then L divided by twice EI. So the total bending strain energy is the summation of the first part, which is having P square A cube divided by 6 EI. So P square A cube divided by 6 EI. And for the second part, we have P square A square L divided by twice. Now from the Castigliano theorem, the deflection along the force P is the first differential of the total strain energy with respect to P. Now if you do that, we have 2P A cube divided by 6 EI plus 2P A square L divided by twice EI. So we have P A square divided by EI, and within bracket we have A by 3 plus L. So if we simplify further, we have P times A square times A plus 3L divided by 3 EI, and that is the deflection at the point C in the vertical direction, because we apply the force along the vertical direction, and then for this force, if we find out the bending strain energy and differentiate that with respect to P, we will get the displacement along that force, right? So you can see how to get the displacement at the point C. Now if we plan to find out the rotation at the point C, so if we wish to find out theta C, then we have to apply a dummy moment here, and then we have to repeat the same exercise, and if we differentiate total bending strain energy with respect to M, we will get theta C. Obviously we have to put M equal to 0, and that will give us theta C. You can take this as an exercise and solve that problem, right? Okay. Now you have seen how we can use Castigliano theorem to solve the displacement and rotation at a particular point, right? Now let us take a different example. So this is our example 2. In this example, we have a beam, a cantilever beam of length say L. So we have AB as the cantilever beam, and we also have a prop at the end B. Its length is L and flexural rigidity is EI. The beam is subjected to a UDL of intensity omega. Now, for this beam, our task is to find the rotation theta b. Now, if you note this structure, due to the presence of this prop here, we cannot solve this structure using equilibrium equation alone, right? So we don't know what is the reaction here, which is RB. So for this problem, we have to solve the reaction at the end first, and then we'll see how we can find out the rotation theta b. Okay, so for that, let us consider a section at a distance x. Now we can find out mx, which is equal to RB times L minus x. Minus, because this is a sagging moment, minus we have omega L minus x whole square divided by 2. Okay, now we can find out what is the total bending strain energy, and that is 0 to L m square x dx divided by 2I. So we can put the expression of mx here. So we have 0 to L. In place of mx, we can put RB times L minus x minus omega times L minus x whole square divided by 2. So this is mx, we have to square it, then dx divided by 2I. Now, of course, we can open this bracket and complete this integral, but if we differentiate this bending strain energy with respect to RB, we get the deflection at the point B. Now, if you look at the condition, this is equal to 0 because we have a support there. Now, if we satisfy this condition, we have the differential of UB with respect to RB. So, in place of UB, we can write 0 to L 1 by 2ICI. Then we have RB times L minus x minus omega times L minus x divided by 2 whole square dx. This is equal to 0. Okay, so now we can differentiate this third bracketed term with respect to RB. Now, if we differentiate that, what will happen? This 2 will be in coefficient, and then we have this third bracketed times we have to consider this the differential with respect to RB, so we'll have L minus x. Let us complete that exercise. So we have 1 by 2ICI, then 0 to L, we have 2 times this third bracketed term. So we have here 2 times, within third bracket we have RB times L minus x minus omega L minus x whole square divided by 2. So that is the third bracketed term. Then we have to again differentiate this part with respect to RB. So we'll get L minus x and then dx. This is equal to 0. So what effectively we get? RB is equal to 0 to L, then omega L minus x to the power 3 divided by 2 dx, and in the denominator we'll have 0 to L, L minus x whole square dx. Right. So if you solve this, I can leave this as an exercise. And if you solve this, you get 3 by 4 W times or omega times L. So leave this as a home task. Please complete this exercise and you'll get the reaction. Before we move further, you can see we started with a indeterminate structure, and using Castigliano theorem, we have solved the structure. We now have RB. Then we can also find out the reaction at the end A and also the moment at the end A. Okay. Now, the second part of the problem we have to solve. And for that, the objective is to find out the rotation at the end B, and we do not have a force there acting, and therefore what we do, we apply a bending moment of M. Actually, this is having a sagging behavior. So let us apply the moment in the reverse direction as per the deflection of the beam, right? So this is M. Now we have to repeat the same exercise for the entire length of the beam. We have to find out the bending strain energy, and then we will differentiate with respect to bending strain energy M, and we will put M equal to 0. But now we know RB from the first part, right? So let us solve this problem. So for this problem, we have Mx is equal to, you can see RB times X, or L minus X. Actually, we can now change this to X, and this is L minus X, right? So because we know RB, we can calculate the bending moment at this section from the right hand side. That will be much easier. So Mx equal to RB times X minus, we have omega x square by 2. Then we have a dummy moment. You can see here M. So you also have to add the dummy moment that we have applied, and which is M. Okay. Now for this problem, we can find out what is the bending strain energy. So that is 0 to L. We have mx square dx divided by twice M. And if we differentiate this bending strain energy with respect to M, then we have 0 to L mx dx divided by EI times, we have mx differentiated with respect to M. Okay, so let us complete the task. So we have bending strain energy differentiated with respect to M, and we have on the right hand side of the equality sign, we have 0 to L mx, and in place of mx we can write this expression RB times x minus omega x square by 2 plus M. Okay. So we have RB times x minus omega x square by 2 plus M. And then we have to differentiate mx with respect to M, and which is equal to 1. So what we get? In place of mx differentiated with respect to M, we can write 1 and then dx. So now let us complete this integral. So we have 1 by EI here. So we have 1 by EI, then first term RB times x square by 2 minus omega x cube by 6 plus mx. Zero to L. So we have 1 by EI, and within bracket we have RB L square by 2 minus omega L cube by 6 plus m. Now we have already evaluated the expression for RB, which is 3 omega L by 4. So we can put that expression here. So we'll have 3 omega L by 4. So we'll have 4 times 2. Okay. So at this stage we can put m equal to 0 because that is a dummy moment, and what we get is theta b. So theta b is equal to 1 by EI. Then we have omega L cube divided by 8 times 3 minus omega L cube divided by 6. Okay. So we have 1 by EI and then omega L cube So effectively we have 5 omega L cube divided by 24 EI. So we get the expression of theta b here. And for that, first we need to solve the indeterminate structure. And once we solve that, then we apply a dummy load, as you can see here. So with respect to this dummy load, we find out the bending strain energy and then we differentiate that strain energy with respect to dummy load and point B, and for that we again finally put m equal to 0 to get the rotation at the end B. Okay. Now let us take a different example. In this example, we have a fixed cantilever beam. So this fixed beam is having length L and EI as the flexural rigidity, and then we apply a force P at a distance L by 2 from either support, right? So we have L by 2 here, L by 2 there, and this is AB. Now for this structure, we have to find out the reactions at the end B. Okay. Now you can see the boundary condition tells us that the displacement at the end B is 0. Also, because we have a fixed support, rotation at this end is also 0. So what we can do, we can actually redraw this structure. So left end we keep it as is, and the right end we replace with a reaction R and a bending moment M. So this is the end A and end B. And we have the point load P at the middle, which is at L by 2 from the either side, right? Now for this problem, we can consider a section at a distance x. So mx is equal to r times x minus m. Now, let this point, the midpoint, be C. So, consider BC. So, bending strain energy within the segment BC is equal to 0 to L by 2. And then we have mx square dx divided by twice here. So this is equal to 0 to L by 2. In place of mx, we can write rx minus m whole square dx divided by twice here. Now, we can consider the segment AC. So, now consider AC. So, for this segment, we have mx is equal to, again, Rx. Let this section x is at a distance x. So the bending moment at this section is Rx minus m minus, now we have this load P, and the distance between the point P and the section at a distance x from B is x minus L by 2. Now, for this part UAC, we can find out the bending strain energy, and that is L by 2 to L mx square. So we have Rx minus m minus P times x minus L by 2. Times dx divided by di, twice ei. Okay. So the total bending strain energy is the summation of these two integrals. So first one we have 0 to L by 2 Rx minus m whole square dx by twice ei. Okay. So we have Rx minus m whole square dx divided by twice ei. And the second part is L by 2 to L, we have Rx minus m minus p times x minus L by 2. Square of this quantity times dx divided by twice ei. Now, if we look at the structure, so if we differentiate bending strain energy with respect to R, obviously that is the displacement at that point, and as per given boundary condition, it is 0. So effectively what we do, we differentiate the total strain energy with respect to R and equate it to 0. So if we do that, then what we have here, you can see twice x, then Rx minus m divided by twice ei. Dx. Okay. Now the second part will be L by 2 to L. Then first the second bracketed term. So we have Rx minus m minus p times x minus L by 2. Times obviously the derivative of this second bracketed term with respect to R, and we get x here, dx divided by ei is equal to 0. Now we can simplify this expression. So this 2 will be cancelled, and effectively we have 1 by ei. Then 0 to L by 2 Rx minus m times we have x dx. Then from the second integral we have L by 2 to L, and then first part, if you can see, Rx minus m times x dx. Then the remaining last term, we can take it on the right hand side. So let us close the bracket here. Then what we have? We have L by 2 to L, then p times x minus L by 2 divided by ei. Now look at the third bracketed term on the left hand side. So we have ei, then the first part is 0 to L by 2 and second part is L by 2 to L, and we have the same quantity integrated over this range. So effectively what we get? We get 0 to L Rx minus m times x dx. Now on the right hand side, we have 1 by ei L by 2 to L, and we have P times x minus L by 2 times dx. So both sides we can cancel this term, and we can further simplify this expression, right? So let us quickly do that. So the first term is 0 to L r x square dx minus 0 to L, we have mx dx is equal to L by 2 to L, and then we have Px minus PL by 2. So there is a x here. So x here. So Px square, then x here dx. Okay. So now if you simplify this expression, again, what you will get is twice RL cube divided by 6 minus thrice ML square is equal to, you can see here on the right hand side, we can complete this integral and then simplify the expression, and again I leave that exercise for you. So we'll have 14 minus 9 divided by 48 and then PL cube. So effectively we get the first equation. We have two unknowns R and M. So we have twice RL minus thrice M is equal to 5 by 8 PL. So that is the first equation. Obviously, because we have two unknowns P and M, we have to develop one more equation, and that will come from the same ut, as you can see here, and this time we have to differentiate with respect to M, because we have applied a dummy moment here. As you can see, the moment we remove this support, and because of the presence of this fixed support at the end B, the rotation at the end B is 0, and therefore if we differentiate ut here with respect to M and put that equal to 0, we satisfy the boundary condition. Okay, so let us do that. So ut is differentiated with respect to M. Now if you do that, this is equal to 0, and we have, you see the first part here. So we'll have 0 to L by 2 and then you can see the term Rx minus M whole square. So if we differentiate that, we have 2 Rx minus M, and then we differentiate minus M with respect to M. So we'll have minus 1 dx divided by twice EI. So this 2 and this 2 will get cancelled. Then plus we have the second part, and for that we have L by 2 to L And if you look at the expression, it is here. So if differentiate this expression, so we have the third bracketed term, then the same with respect to m, that will offer -1, right? So we have Rx minus m minus p times x minus L by 2. So that is the expression within the third bracket. Then -1, the moment we differentiate minus m with respect to m, dx. And this is equal to 0. So this is the expression here. What we do, we differentiate this square bracketed term, and then the expression we get here. We can actually develop the equation now. For that again, we have EI here. Then we can also cancel EI. So effectively what we have, 0 to L by 2, then Rx minus m times dx plus the second part L by 2 to L, and we have Rx minus m minus p times x minus L by 2 dx. So this is equal to 0. Now again, what we can do is first part 0 to L by 2 Rx minus m dx, and from the second term we have L by 2 to L, and first part is Rx minus m dx, then minus L by 2 to L p times x minus L by 2 times dx is equal to 0. So if we combine these two, we have 0 to L Rx minus m times dx is equal to L by 2 to L p times x minus L by 2 dx. Let us just write it once more. We have 0 to L Rx minus m dx is equal to L by 2 to L, and we have p times x minus L by 2 times dx. So what we effectively have, Rx square divided by 2 minus mx, range is 0 to L, is equal to, we have px square by 2 minus plx by 2, and that we have to evaluate over a range L by 2 to L. So if you do this exercise, we will get RL square minus twice ML is equal to PL square divided by 2 minus PL square divided by 4. So from this expression, we can develop the second equation, which is RL minus twice m is equal to PL by 4. So that is the second equation. So we have the first equation here, which is twice RL minus 3M equal to 5 by 8 PL. So let us just write it here. We have twice RL minus thrice M is equal to 5 by 8 PL. So that is the first equation, right? Now we have two equations, two unknowns P and M, right? We can solve this. Again, I leave this as an exercise for you. You can solve it, and the moment you solve it, you get reaction R is equal to P by 2 and moment M is equal to PL by 8. Now, if you go back to the main structure, you can see we have a point load at the middle, right? And the structure is symmetric about this point C, and therefore we expect the reaction at this point and reaction at this point will be equal, and they are P by 2 and P by 2. And effectively the same result what we get here using Castigliano theorem. Right. So you can see how we can use Castigliano theorem to solve indeterminate structure. In this case, we have this degree of indeterminacy 2, which are at the end B, you can see they are R the reaction and the support moment M. Both of them we have solved using theorem of Castigliano, right? Okay, so we'll continue on solving some more indeterminate structure as we progress in the course. So with that, let us close our discussion in this lecture. Thank you very much.